Hello everyone, welcome back to Must Electronics. This is what building Android looks like from the outside. Thousands of lines scrolling, files being compiled, libraries being linked. Somewhere in this chaos, 800 plus repositories worth of source code is being turned into a bootable Android image. But here is the thing, none of this is random. Every single file being compiled right now, every compilation flag, every dependency, every output path, all of it was figured out before a single line of code was compiled. There is a whole build system running underneath this that most people who build AOSP never bother to understand. And that is a mistake. Because once you understand it, you can add your own code to the build, create your own modules, and modify Android in ways that would otherwise take you days to figure out. That is what this episode is about. All comments are in the description below. Let's get into it. Before we look at what Android uses, let me quickly explain the problem it solves. Because if you have ever used Make in a small project, you might be wondering why Android needs anything more than that. Let me show you what a traditional Make file looks like. This is main.mk file, the entry point of the old Android build system. Look at it. Variables defined on top of variables, rules that depend on rules that depend on other rules. Android used this system for years. It is called the make based build system. And it worked, but it had serious problems. Problem 1, speed. Make is single threaded by design. To get parallelism, you have to tell it explicitly. And it is not great at figuring out what actually needs to be rebuilt. Problem 2, correctness. Make tracks dependencies through timestamps. If a file was touched but not actually changed, make still rebuilds everything that depends on it. That wastes time constantly. Problem 3, scale. With 800 plus repositories and tens of thousands of build targets, the old make build was slow to even start. Just reading all the make files took several minutes before a single file was compiled. Google knew this had to change, so they built Soong. Soong is Android's modern build system written in Go. It replaced the old make based system starting from Android 7.0, and by Android 14, it handles almost everything. The idea is simple. Instead of writing make files, you write Android.bp files, blueprint files. Soong reads every Android.bp file across the entire source tree and builds a complete dependency graph of everything that needs to be compiled. Then it hands that graph to Ninja, which does the actual compilation in parallel. Let me show you where Soong lives. This entire directory is the Soong build system itself, written in Go. The key thing to understand is the two-step process. Step 1. Soong reads all the Android.bp files and generates Ninja build files. Step 2. Ninja takes those build files and runs the actual compilation. Soong is the planner and Ninja is the executor. Let me show you where the Ninja build files get generated. The .ninja file is enormous. It contains every single compilation command for the entire build system, every compiler invocation, every linker call, every copy operation, all pre-computed and ready for Ninja to execute. This is why build can run thousands of parallel jobs efficiently. Ninja knows the exact dependency graph before it starts. It never has to stop and think about what to do next. Now the part you actually need to know to work with AOSP is the Android.bp file. This is how you tell the build system about your code. Every module in Android, every library, every app, every binary is described in an Android.bp file. Let me open a real one. Let's look at the one for the settings app. Look at this structure. This is blueprint syntax. You describe a module, you give it a name, you list its source files, you declare its dependencies, you say what kind of thing it is, an app or library or a binary. And that is it. Soong reads this and knows exactly how to build the settings app. No makefile, no shell scripts, no manual compiler flags. Just a declarative description of what you want. Let me open another one, something simpler. Let me find a small native library. This is a C++ library definition. The type is cc underscore library, a shared and static C++ library. Name is the module name. This is what other modules use to depend on it. Defaults are declared here, and this default is defined here. Sources is the list of source files, and this is also linked with another defaults. So here we can find shared libs, which lists what this library itself depends on. So here this depends on libcutils and liblog. See how clean this is, no makefile variable soup. You read this file and you immediately understand what libutils is, what it compiles and what it needs. Now let me show you the common module types you will see everywhere. cc underscore binary, a C or C++ executable. Init, ADB, fastboot, these are all cc underscore binary. cc underscore library. A C or C++ library can be shared, static, or both. cc underscore library shared. It is a shared library only. And then Java library, Android app, which is an Android application, and the output will be APK. Pre-built etc. This copies a file into the system image, config files, scripts, and so on. File group groups source files together so multiple modules can reference them. These 7 types cover 90% of what you will see when reading Android.bp files across the source tree. The part that makes the build system actually powerful is dependencies. Every module declares what it needs. Soong uses those declarations to build the full dependency graph, figuring out what order to build things and which modules need to be rebuilt when you change something. Let me show you a real example. Let me use logcat, the command you use every day with ADB. This is the android.bp file for the logcat binary. The type is cc underscore binary, a C++ executable. The name is logcat. This is how other modules reference it. Now look at shared libs. There is libbase, libutils, libprocessgroup, libprotobuf, and in static libs there is liblog, each defined in its own android.bp file somewhere else in the tree. When Soong sees this, it knows before building logcat, build all of these libraries first, and if any of them change, rebuild logcat. This is the dependency graph in action. Now here is a practical question. What if you want to know everything that depends on liblog? How many modules across AOSP are depending on it? Liblog is one of the most depended upon modules in all of AOSP. Basically, every process that logs anything depends on it. Change a single line in liblog and Soong will correctly identify every module that needs to be rebuilt. That is correctness that May could never guarantee. Now let me show you something that always surprises people seeing it for the first time. To build all of Android, 800 plus repositories, tens of thousands of files, you run exactly 3 commands. So the first one is dot space build slash env setup.sh, which loads the Android build environment into your shell. It adds helper functions like lunch, mmm, and reads the device configurations from every device or directories in the tree. The next one is lunch command. Lunch is where you select what you are building and for what device. AOSP underscore RPI4 is the product name. It comes from AOSP underscore RPI4.mk file in device BRCM RPI4 directory. AP2A is the build ID. It identifies which Android release this is. Userdebug is the build variant. Let me explain build variants because they matter. User is a production build which is locked down where root access is disabled. User debug is same as user but with root access and debug symbols. This is what we use. ENG is the engineering build where everything is unlocked, more verbose and slower. For development and testing, always use user debug. After running launch, look at what it prints. Target product is AOSP underscore RPI4. Target build variant is user debug. Target arc is ARM64. The entire build system now knows exactly what it is building. Every Android.bp file will be evaluated with these values in mind. That brings up to the third command. This starts the build. Notice we are not building everything, just the three images we need: boot image, system image, vendor image. These produce boot.img, system.img, and vendor.img. The -j $nproc flag tells make to use all available CPU cores. Now watch what happens in the first few seconds of output. Those lines, the percentage, the count, the file being compiled, that is Ninja. Not make, not Soong, Ninja. Here is what actually happens under the hood. Soong runs first. It reads every Android.bp file across the entire source tree and generates a Ninja build file, a complete pre-planned list of every compilation command in the right order. Then Ninja takes over and executes that plan in parallel across all your CPU cores. Soong is the planner, Ninja is the executor. Make just kicks it all off. We are not waiting for the full build right now. For me, it took around 5 to 6 hours. It all depends on RAM and CPU cores you have. We will run all this live in the next episode. Once the build completes, there is one final step: assembling the flashable SD card image. RPI4 mkimg.sh is a shell script specific to the Raspberry Pi build. It takes the boot IMG, system IMG, and vendor IMG that make just produced and packages them together into a single flashable image that one you write to the SD card. That is the complete build pipeline from source to a bootable Android image. Here is something that will save you enormous amount of time when you start modifying Android. The full build took around 5 to 6 hours. You do not want to run it every time you change a single file. The mm command builds only the module in the current directory, no more, no less. Let me demonstrate. Let me go into the settings app directory. After running mm in settings directory, it started building only settings module, not the whole Android tree. And here is something worth watching closely. If you run a second time immediately without changing anything, Ninja prints Ninja no work to do. As I have already built settings module before, I am getting the same result. That is the incremental build working exactly as intended. Nothing changed, so nothing is rebuilt. The moment you edit a source file and run again, only the files that depend on your change get recompiled. That is the power of proper dependency graph. It still respects all the dependencies. It will rebuild any dependency of settings if needed, but it will not touch anything unrelated. This is how Android platform developers work day to day. Make a change, run test it, and repeat. There is also command which takes a directory path as an argument, so you can build any module without changing directory first. Let me go back to the root directory. So I'll run with settings path. Same result. More convenient when you are working across multiple directories. And if you want to build multiple modules at once, say the settings app and its underlying libraries, you can pass multiple paths to mmm command. Now here is something important that trips people up. MM and MMM do not update the system image on your Raspberry Pi. The output, that is the APK or binary, lands in out, target, product, RPA4 directory, but the system.img sitting on your SD card knows nothing about it. To actually test the change on the device, you have two options. Option 1. Push it directly over ADB while the Raspberry Pi is running. For an APK like settings that looks like this. We can install APK using ADB install and the APK path. So once the Raspberry Pi is connected to your system, we can install settings APK using this command. For a native binary, you would use ADB push to copy it to the right location. Option 2. Rebuild the full system image and refresh the SD card. This is required for deep system changes, things like init, core libraries, or anything that needs to be on the partition from boot. The ADB push workflow is something we will do practically in a future episode when we start making real modifications to Android. For now, just know that gives you a fast compile, not a fast flash. This is the workflow you will use constantly once we start modifying Android in the upcoming episodes. One more thing worth understanding: where does the output actually go? Every build output goes into one directory, that is out directory. Out host directory contains tools built to run on your Linux machine. Things like ADB, Fastboot, AAPT, DX2OAT, tools you use during development. Out target directory contains everything built for Raspberry Pi, the actual Android image. This is what we saw at the beginning of episode 3. Boot.img, system.img, vendor.img, the Raspberry Vanilla AOSP 14 flashable SD card image. Everything under out directory is generated entirely by the build system. You never manually put anything there. And here is an important thing to know. Out directory is fully safe to delete. If your build gets into a broken state, you clean it like this. Make clean. So this command deletes the entire out directory and starts fresh. And if you want to clean a specific module, then you can give make clean hyphen module name. So I'm giving settings here. This only cleans the settings module's compiled output. All other output in out directory are completely untouched. Next time you run in the settings directory, it recompiles settings from scratch. Dependency libraries are already built, so those are skipped. Only settings source files are recompiled. This is the right tool when you hit a strange build error that a clean rebuild can fix without throwing away the entire build. You now understand how Android builds. Let me summarize what we covered. The old make system worked but didn't scale. Soong replaced it. It reads Android.bp files and plans the entire build. Ninja executes that plan, compiling thousands of files in parallel. Four commands run the whole thing. Dot space build envsetup.sh to load the environment. Launch to pick your device and build variant. Make boot image, system image, vendor image to build the three images. RPA for mkimg.sh to package them into the final flashable SD card image. Day to day, you use or MMM to build just the module you're working on. All output goes to out directory. It is safe to delete and regenerate at any time. In this episode, we ran build commands briefly just to see what they look like. But we did not wait for the build to finish, and that was intentional. Episode 7 is where the full build happens. We run all four commands live, and this time we let it go. Around 5 to 6 hours of compilation condensed into a time lapse. The moment the build finishes and boot.img, system.img, vendor.img appear, we walk through what each image actually contains and what it does. The build system explained in this episode is the exact machine running in the background during every second of that compile. Then the episode 8, the exciting one. We take those images, flash them into an SD card, slot it into the Raspberry Pi, and watch Android 14 boot from source code you built yourself. If this video was helpful, please like the video and subscribe to Must Electronics.